Hello, this is TianlaiGu. This video is for my real-time interactive demo based on 3D Gauss splitting. For this project, I reproduced the 3D GS pipeline using the GSplot library and integrated it into a Visual WebGL engine. My technical contributes focus on three parts: implementing a customer structure similarity loss, which also called SSIM loss, optimization GPU memory footprint using 4-byte precision, and assess the mathematical limitation of spherical harmonics in handling specular reflection. Let's first look at the impact of our custom SSIM loss. On the screen, you can see the baseline model trained with poor L1 loss, the background plant, and the texture suffering from the blurring artifacts. You can see the grass and the plant in here, and this, the rendering is very blur. And now I'm switching to the model trained with our combined L1 and SSIM loss. The high frequency detail and the physical boundaries are astonishingly restored. But how does the model achieve this? If we look at the system matrix, we can see the hidden cost, extreme capacity expansion. To meet the strict structure constructor of SSIM, the optimizer tracked the mass densification. The number of Gaussian primitives skyrocketed from 730,000 to over 5.1 million. This significantly improved clarity, but it drops our frame rate and heavily burdens the VRAM bandwidth. To prove that geometry capacity is foundation of rendering quality, I ran a sparse experiment by increasing the densification threshold. In this tab, as you can see, the image degrades into black color blocks because there are simply not enough primitives. Speaking of primitives, managing over 5 million Gaussians requires strict memory control. In my implementation, I strictly aligned the registration pipeline to 4 bytes stand float 13.2 precision, blindly using 8-byte float 16.4 for spherical harmonics would double the GPU memory footprint and crash the system during backpropagation. Finally, let me show you an interesting counter-intuition phenomenon I discovered using this interactive viewer, the radiance bake effect. Look at these material spheres. Even so, the model used third-order spherical harmonics, which SH equals 3, the parameter, has dozens of parameters to simulate a highlight flow. The specular highlights looks like regular stickers. They don't have true physical parallax when I move the camera. Surprisingly, when I force the model to using SH equals 0, I set the parameter SH equals 0, which stripped away all reflective capabilities. The visual output was almost identical. This proved a core mathematical limitation because low-order SH cannot fit extremely high-frequency specular. The optimizer cheats. It bakes the highlights directly into the diffuse base color to reduce the photometric loss. In conclusion, this demo implements real-time 3D GS interaction. highlights the trade-off between structural loss and model capacity, and exposed the inherent flaws of spherical harmonics on and expose the inherent flaws of spherical harmonics on reflective surface. Future improvements should consider introducing PBR materials. Future improvements should consider introducing PBR material properties.